Hello everyone. Today I will discuss about exact differential equations. Exact differential equations. A differential equation dy by dx is equal to f of x y, that is dy by dx is equal to function of x y f x y of first order and first degree can be expressed in the form m of x y dx plus n of x y dy equal to 0 or m dx plus n dy equal to 0. Where m and n are functions of x and y. If m dx plus n dy is expressible in the form of du, where u is a function of x and y, it is said to be exact, and the equation m dx plus n dy equal to 0 is known as an exact differential equation. If the equation m dx plus n dy equal to 0 is exact, then there exists a function u of x y u x y such that du is equal to m dx plus n dy equal to 0, and the general solution of the equation is u is equal to c for some arbitrary constant c. Now, example 1, the differential equation e to the power x cos y dy plus e to the power x sin y dx equal to 0 is an exact differential equation, since it can be obtained by direct differentiation from its solution function e to the power x sin y c, because if we differentiate this equation e to the power x sin y is equal to c, then we will get e to the power x cos y dy plus e to the power x sin y dx is equal to 0, that is this equation. So, e to the power x sin y is equal to c is solution of the equation e to the power x cos y dy plus e to the power x sin y dx equal to 0. Therefore, this equation is an exact differential equation. Example 2, the equation 3x cube 3x raised to the power 3 y square dy plus 3x square y cube dx equal to 0 is an exact differential equation, as 3x cube y square dy plus thrice x square y cube dx equal to d of x cube y cube. Its general solution is x cube y cube equal to c, because if we integrate this, then we will get x cube y cube is equal to some arbitrary constant c. Therefore, this equation is an exact differential equation. The equation y dxy plus x dy is equal to 0 is an exact differential equation, because y dx plus x dy is equal to d of xy. If we integrate this, then we will get xy is equal to c. Therefore, solution of this equation is xy is equal to c, and this equation is an exact differential equation. Theorem: the necessary and sufficient condition that Mdx plus Ndy is equal to 0 is exact is del m by del y is equal to del n by del x. That is, m dx plus n d is equal to 0 is exact if and only if del m by del y is equal to del n by del x. Proof: suppose that m dx plus n dy is equal to 0 is exact, then we have to show that del m by del y is equal to del n by del x. Since m dx plus n dy is equal to 0 is given to be exact, therefore, m dx plus n dy is an exact differential of some function, say u x y, that is m dx plus n dy is equal to du. The expression for du is given by du is equal to del u by del x into dx plus del u by del y into dy. The expressions must be identical, and hence dx dy being independent increments. So, m is equal to du by dx and n is equal to del u by del y. Therefore, del m by del y is equal to del upon del y of del u del x, because m is equal to del u by del x. Therefore, differentiating m partially with respect to y, we have del m by del y is equal to del of del y into del by del y of del u by del x, which gives del 2 u by del y del x. And similarly, if we differentiate n partially with respect to x, then we have del n by del x is equal to del by del x of del u by del y, which gives del 2 u by del x del y. Then del m by del y is equal to del n by del x, provided that the equivalent expressions del 2 u by del y del x and del 2 u by del x del y are continuous. Therefore, del m by del y is equal to del n by del x, provided del 2 u by del y del x and del 2 u by del x del y are continuous. Now, assuming that del 2 u by del y del x is equal to del 2 u by del x del y, then we have del m by del y is equal to del n by del x, which proves the necessary condition, that is, which proves that the condition is necessary. Now, we have to prove the sufficient part. For this, conversely, we suppose that del m by del y is equal to del n by del x. We have to show that m dx plus n dy is equal to du for some function u of x y, that is m dx plus n dy is an exact differential equation. Let phi be a function which is equal to integration of Mdx, where the integration is performed on the assumption that y is constant. If we integrate this quantity Mdx, then we will consider y as a constant, because this expression is integration with respect to x, where m is a function of x and y, but we will consider y as a constant. Therefore, m is equal to del phi by del x and del to phi del y del x is equal to del to phi del x del y is equal to del m by del y, and since del m by del y is equal to del n by del x, and del by del x n minus del phi del y is equal to 0. Therefore, n minus del phi by del y is constant so far as is concerned, that is function of y, say f of y. Hence, n minus del phi by del y is equal to f y, that is n is equal to f y plus del phi by del y. Now, take the function u x y such that u is equal to phi plus integration of f of y dy. Therefore, if we differentiate this quantity with respect to y partially, we have del u by del y is equal to del phi by del y plus f of y, which is equal to n, since n is equal to f y plus del phi by del y. Therefore, del u by del y is equal to del phi by del y plus f y is equal to n. Since m is equal to del phi by del y is equal to del u by del y, as u is equal to phi plus integration of f y dy. Therefore, m dx plus n dy is equal to del u by del x dx plus del u by del y dy is equal to du, which is a perfect differential. Therefore, the equation 1 is exact and the condition 2 is therefore sufficient, which proves the theorem that m dx plus n dy is equal to 0 is an exact differential equation if and only if del m by del y is equal to del n by del x. Working rule for solving the equation m dx plus n dy is equal to 0 when it is exact. Number 1, integrate m dx as if y is a constant. Number 2, integrate n dy as if x is a constant, but then delete those terms already obtained in the expression 1. The sum of these integrals will give a function, say u x y, such that du is equal to m dx plus n dy. Fourth, when u is obtained, then u is equal to c is the required solution. Therefore, to solve any equation Mdx plus Ndy is equal to 0 which is exact, these 4 conditions should be followed. Now, example 4. Solve the equation x square minus 4 x y minus 4 x y minus 2 y square into dx plus y square minus 4 x y minus 2 x square into dy is equal to 0. Solution. Here m is equal to x square minus 4 x y minus 2 x square. This coefficient of dx is equal to m. Similarly, coefficient of dy is n is equal to y square minus 4 x y minus 2 x square. Therefore, del m by del y is equal to minus 4 x minus 4 y is equal to del n by del x. Therefore, according to theorem, the given equation is exact. Now, by the working rule 1, integrate m dx. We have integration of m dx is equal to integration of this quantity into dx, that is x square minus 4 x y minus 2 y square dx is equal to x cube by 3 minus 2 x square y minus 2 y square x, assuming y to be constant. Secondly, y square dy is the only term in the n dy free from x, because 4 x y contains x and 2 x square contains x. So, y square dy is the only term in n dy which is free from x, and we will integrate this quantity y square dy with respect to y. So, integration n dy is equal to integration y square dy free from x terms, which gives y cube by 3. Therefore, the solution is x cube by 3 minus 2 x square y minus 2 y square x plus y cube by 3 equal to c, where c is an arbitrary constant of integration. By simplification, we have x cube minus 6 x square y minus 6 x y square plus y cube is equal to thrice c. Thank you very much for watching this video. Please don't forget to subscribe my channel. Please like, share and comment. Please press the bell icon to get notifications.